Dear students, today we'll see what do we mean by aliasing effect. Now, before going to see aliasing effect, we should know what we studied in sampling theorem. So, in sampling theorem, we studied that sampling frequency Fs should be greater than or equal to twice the highest modulating frequency, so that we can recover the original signal back from its samples at the receiver without any distortion. So that was our basic condition for sampling theorem, and it was also called as Nyquist criteria. Now here, to study aliasing effect, we should consider three cases. The first case what we should consider is, number one, when Fs, that is sampling frequency, is greater than twice Fm, twice the highest modulating frequency. If this is the case, how will the frequency spectrum of the sampled wave look like? Then if you draw that frequency spectrum, you can see, say this is frequency line, this is your zero line, this is the first centered frequency, second centered frequency, this is frequency, this is minus Fs, and this is minus 2Fs. Now if you draw the frequency spectrum of the sampled wave for the condition Fs greater than 2Fm, you can see that it will look like this. This is so here this is 0 to Fm and this is 0 to minus Fm. So there was a gap between frequency spectrum of adjacent pulses. So if you see, this was your starting frequency spectrum of pulse of train multiplied by the analog signal frequency spectrum of that, and here you see your original signal is placed. Your original signal is placed from 0 to Fm. You can also take a 0 to minus Fm because it is a replica of that, but we will consider this 0 to Fm. So this was your original signal, and if you pass this waveform, this frequency spectrum, through a low pass filter whose cutoff frequency is Fm, then you can reconstruct this original signal back. You can obtain your original signal back. This was your sampling of low pass signals, what we studied. Now second case, if you take case number 2, sampling frequency is equal to 2Fm. So it is exactly satisfying the Nyquist criteria. It is ideal condition, which cannot be practically possible because you cannot build practical filters for this. Now here, if you see, the spectrum will look like this. If you take this as 0, this is your first centered frequency, this is your second centered frequency, this is on the negative side, first centered frequency and second centered frequency. The frequency Fm will be little stretched. Then you can see like this, then you can see like this, you can see like this, you can see like this. All the frequency spectrums will come correctly. All the frequency spectrum will come correctly, but there will be no such gaps between the frequency spectrum. This will be an ideal condition for which you cannot have practical filters. So ideally, filtering you can do, you can reconstruct this original signal. This is all ideal case 0 to Fm, but you cannot practically do it. But this is your basic Nyquist criteria. Now if you take the third case, where the sampling frequency is less than 2Fm, that is, it is undersampled. It is undersampled, and if you draw a frequency spectrum for that, if you draw a frequency spectrum for that, you can see this is 0, this is the first centered frequency, this is the second centered frequency, this is on the negative side, sorry, this is on the negative side, this is minus 2Fs, this is Fs. Now if you draw the frequency spectrum over here, the Fm part 0 to Fm and 0 to minus Fm will be stretched a little like this. and then the next will be like this. the next will be like this. Here also you can see it will be like this, and here also you can see it will be like this. Now here in this case, if you see, this is your FM. This is FM. And now here if you see the frequency spectrum of the first term and the second term of the adjacent pulse will overlap. This is overlapping. So this part to this part, this is the higher part of your signal. This was your signal. This, if you mark it, this was your signal. So if you can see, this was your signal. This was your signal. So the highest part of the signal is overlapped by the lower frequency of the next spectrum, of the next double sideband spectrum, which is centered as for Fs. That lower frequency of this spectrum is overlapping higher frequency of your original signal. So this higher frequency of the original signal take the identity of the lower frequency of the next double sideband. So this overlapping is called as aliasing effect. Now for this, you cannot build any low pass filter and reconstruct your original signal back because of this overlapping. So this is an error. This is an distortion which takes place because you are not maintaining the sampling frequency Fs is equal to or greater than twice FM. You have taken sampling frequency as Fs less than 2 FM. Because of this undersampling, this overlapping takes place. And in this overlapping, what is happening? The higher frequency component of your original signal, is taking the identity of the lower frequency component of this. This is lower frequency component of the next double sideband. That identity it is taking. Now this overlapping is called as aliasing effect. This you can call it as aliasing effect. And this is the effect you are getting because of undersampling. Because you are taking the condition sampling frequency is less than twice the highest modulating frequency.